Morning, nerds, and welcome to the end of Unit 2.13, where we are going to be actually solving exponential and logarithmic inequalities. Okay? Exponential and logarithmic inequalities. And here is going to be the idea. Rather than memorizing a whole bunch of rules about when it's exponential, when it's logarithm, and stuff like that, what we're going to do is we're going to manipulate our exponentials and we're going to manipulate our logarithms until we have bases that are greater than 1. Because as long as we have bases greater than 1, our inequalities will always point the same direction that they did when we began. Okay? Meaning we won't have to worry about any weird properties that would turn an inequality symbol over, other than simply dividing or multiplying by a negative number, which you've been practicing since Algebra 1, hopefully. So, once again, manipulate whatever you have to manipulate to make sure that all of your bases, exponential and logarithmic, are greater than 1. That's going to be the process. Boom. So just find the solution set of this inequality, check for extraneous solutions, verify your answers with a graphing utility. Well, we're always going to be on the lookout for extraneous. And unfortunately, this whole graphing utility thing is remarkably difficult to use to verify, because when you graph these things on Desmos, it can't even zoom in far enough for you to see that this works. So rather than wasting time trying to find a window that'll work, and by the way, I tried in period 2, and I even called it scorched earth. I went from 0 to 0.001 with my scale going 0.0001, and still that wasn't zoomed in far enough. Desmos caps out at scientific notation to the -7th power, and that still wasn't enough. I have no idea how far we have to zoom in, but for all I know, it could be like 10 to the -20th. So because of that, we're not going to bother wasting our class time on that, just so you know. Okay? Okay. Alrighty. So, exponential inequalities, we approach them the same way that we approach exponential equations. We want the same base on both sides, right? Same base on both sides? Lucky for us, the number 125 is a power of 5. We have a power to the power situation on the right side, which means we need to multiply those exponents. Don't forget to distribute. My blue pen is not behaving. Is it running dry? Nope. Just not behaving. Since we have exponential base 5 on both sides, and like I said, those bases are greater than 1, we can use log base 5 on both sides to cancel these two 5s. We don't have to show that work. We all know that it would have canceled the 5 on both sides and left us with x. See, my blue pen is just not behaving correctly. X is greater than 3x plus 18. Subtract 3x from both sides and divide by -2. Remember, dividing by a negative turns an inequality over. Boom. And there it is. Because exponential functions have domains of all real numbers, there will not be anything extraneous about the solution set. It is all the numbers that are less than -9. Boom. There it is. Pretty darn easy, right? Okay. Remember what our goal is. We always want to manipulate our bases so that they are greater than 1. That way our inequality symbols behave the way we think they do. Both of these numbers are powers of 3. Three to the -1, and this one will be 3 to the -3. There. Power to a power on both sides. Make sure you distribute. And because we have exponential base 3 on both sides, which is greater than 1, we could use log base 3 of both sides, cancel both of those 3's, leaving us just the exponents. If you add 3x, you get positive x. And if you add 9, you get 18. X is less than or equal to 18. There it is. Cool beans, huh? It's not that bad. Not that bad at all. But that's because exponentials, they play nice. You know, I mean, they have domains of all real numbers. That makes your life really, really easy. Now, that's not true for logarithms. You know, logarithms have restricted domains. So when we go to do these kinds of problems with logarithms, we always have to keep in mind the rules of the domains. We ready to flip over and do some logarithm stuff? Questions, comments, concerns about exponentials? Or are we good? We're Gucci. All right. Let's go to the logarithms. Now look, there are all kinds of rules that you could try to memorize. I mean, there's all kinds of rules that you could try to memorize involving logarithmic inequalities. But if you're anything like me, memorizing a whole bunch of rules and hoping that you never forget them is not going to work out very well. I try to memorize as little as possible. So we're going to stick to make sure the bases are greater than 1. Because as long as you manipulate the bases so that they are greater than 1, your inequalities stay what we expect them to be. So just like exponentials, we will always manipulate so that our bases are greater than 1. And in order to pull that off, you're going to have to remember one of the things that we quote-unquote discovered when we were practicing our change of base. So if the base is not greater than 1, if it's between 0 and 1, flipping it over puts a negative sign on the front. And we, quote-unquote, discovered that property when we were working with change of base. And in case you don't recall that, let me grab one of these tardy passes out of the trash can and just re-engineer it for you. Take this and use change of base. But this could be written as b to the negative 1. And our expanding property says we could bring this negative 1 down to the front of that logarithm. And it doesn't matter if the top of a fraction or the bottom of a fraction is negative. Overall, that makes it negative. Log of a over log of b gets you back to log base b of a. And we did that when we were working with change of base. That was also when we found out that switching the argument in the base just gives us the reciprocal of our logarithm, if you can remember that. It's one of those setups. But this idea right here saves us from having to memorize a ton of stuff. Know one rule. You want bases larger than 1, and you don't have to memorize all the rest of that stuff. Pretty cool, huh? All right. And that was partially brought to us by Dan Lee, helping me remember that that was a thing. Because I'd never put two ideas together, this idea together with what we're doing right now. Cool beans. First thing you want to check, are the bases greater than 1? They are? Yay! Life is good. I don't have to do any manipulation that way. Second thing you want to check, domain. The argument of every logarithm must be positive. So this thing's domain is x is greater than 0. Now we can go forward with solving. Just like we did on the previous page where we needed the bases to match, that way we could use the logarithm to get rid of them. We need the logarithms to match, that way we can use an exponential base to get rid of them. But we can't cancel a logarithm until it's alone, which means this pesky 2 must be moved into the exponent position of the argument. that would give us log base 2 of 9 is greater than log base 2 of x squared. At this point, we can use exponential base 2 to cancel our log base 2's on both sides of the inequality, leaving us with 9 is greater than x squared. Be careful. This is a quadratic inequality. Quadratic inequalities need to be solved using sign diagrams. That's old knowledge. You guys remember doing those earlier in the year? The idea is factor it. So get it equal to 0. In this case, it would be less than 0. And factor. It's a difference of two squares. Instantly factors to x plus 3, x minus 3. Boom. Great. We must use sign diagrams to solve quadratic inequalities. So we put our critical values on a sign diagram, which would normally be positive 3 and negative 3, correct? Because it's what makes the insides equal 0. So for here, I would have x equals negative 3, and here I'd have x equals positive 3. But before I get too busy with this, tell me, what's the problem with that, Adi?
The x can't be negative or 0.
That means our sign diagram actually does not exist to the left of x equals 0. In fact, at x equals 0, we have an asymptote. So none of this exists. We do still have two zones, a zone between 0 and 3 and a zone after 3. So we test them like we always have, and we'll be looking for negatives because that's what's less than 0. So we can't use x equals 0 because the graph doesn't exist at x equals 0. So use x equals 1. 1 plus 3 is positive. 1 minus 3 is negative. When you multiply a positive and a negative, you get a negative. Grab x equals 4. 4 plus 3 is positive. 4 minus 3 is positive. Product of two positives is a positive. And we were hunting for numbers that were less than 0, which are negative numbers. So this is our solution set from 0 to 3. Ta-da! Not too bad, right? Yes, sir. Oh, because we're looking for a quadratic that's less than 0. That's why we're looking for negatives. So when you set up a sign diagram, what you're actually doing, this negative symbol and this positive symbol, is telling you if your y values of that graph would have been positive or negative. So if you were to graph this quadratic right here, it's an upwards facing quadratic. Here, I'll just sketch it over here. It looks like this. But we're not allowed to use anything to the left of 0. So you're saying, where are that quadratic's y values lower than 0? That would be negatives. So anything between x equals 0 and x equals 3. Cool? But this saves us from having to actually graph it. So we're only going to have to use the sign diagrams when we're dealing with quadratic inequalities. Or let's just say I really, really hated you, polynomial inequalities in your logarithms. I'm not going to do that because it's mean. But you could. You could. You know, I don't know. We've never seen an AP exam, so we don't know. Checking this one out, what I see is a base that's larger than 1. So yay, I don't need to do any manipulations there. But I do need to find out what the domain is. My argument cannot be negative. So we say 2x plus 1 had better be greater than 0. Bless you. Subtract 1 and divide by 2. Bless you. Okay. Our domain is x is greater than negative 1/2. So all of our answer choices had better be greater than negative 1/2. Adi, you made a weird face when I said that. You okay? Okay. Let's work it out. Let's cancel the log base 2 with an exponential base 2 on both sides. Two to the third is 8. Yes, Charlie?
Why didn't the sign flip?
When? You mean here in red?
Yeah, but
Because I divided by a positive number.
oh.
The only time you flip your sign over is if you multiply or divide by a negative. But adding and subtracted won't change it. So it's strictly this multiplying and dividing by negatives that flips our symbols over, okay? Subtract 1 gets me 2x is less than or equal to 7. Divide by 2 gets me x is less than or equal to 7 over 2, which is 3.5. But there it is. Our solution set is all numbers less than or equal to 7 over 2, but my domain begins at negative 1/2 and only goes to the right, giving us an overall answer set of from negative 1/2 not inclusive all the way up to 7/2 inclusive. What do you think? It's not bad, is it? It's really not bad. In fact, it's so easy that I've baked up a harder question that we're going to write on the back. Oh, stop. Quit. Wah. You guys ready for part C? What we notice here is that these bases are not greater than 1. So we're going to use the property that says if you use the reciprocal base, then that just puts a negative sign on the front of the logarithm, which means I'm going to put a negative sign on the front of both of these logarithms. Negative log base 2 of 2x minus 3 greater than or equal to negative log base 2 of x plus 5. Darn those pesky negative signs. Lucky for us, there's a negative sign on both sides of the equation. That means we don't need to move them to the exponent position of these setups. Because there's one on either side, we can just divide both sides by negative 1. But that will flip that inequality symbol over. Okay? Cancel your log base 2's with exponential base 2's. Leaving us with 2x minus 3 is less than or equal to x plus 5. Subtracting x and adding 3 gets you x is less than or equal to 8. But there are two logarithms here, and these two logarithms have their own domains. What we have to do is make sure that we only choose values that break no domains. So we're going to look at our two different domains, and we're going to figure out which one we can play with. We know that 2x minus 3 had better be positive, and we know that x plus 5 had better be positive. Add 3 and divide by 2. X had better be bigger than 1.5, 3 over 2. This one says subtract 5. X had better be greater than negative 5. Which of these two domains is the one that I have to use?
The one of 3 over 2 because does it already have to be above 0?
Well, no, it doesn't have to be greater than 0. There's no rules about that. The argument has to be greater than 0. Your job is always to use the more restrictive domain, and I've used that terminology early on in the year. Do you remember? The more restrictive domain. We have to use this one. Reason why. Doesn't this one allow x to be 5? Not 5, what's wrong with me? This one allows x to be 0, right? Okay, so if you try to use x equals 0, you break a logarithm. This one allows numbers between negative 5 and positive 3/2. And this one is not allowed to use any of those numbers. So this is the more restrictive domain. This is the one you have to use. The more restrictive is the one you want to use. So our answer set begins at 3 over 2, which is 1.5, and ends at 8, including the number 8. There it is. So what we're going to do, because that was a fast lesson and I think a relatively easy lesson, as long as you always make sure your bases are greater than 1, what I wanted to do was make a challenging question. So put a challenging one on the back. And by the way, it could be much more challenging than the one that I'm about to write on the back. Before we flip over to do anything that's over and above what even the CED wants us to do, are there any questions about logarithmic inequalities?
Oh, actually, it's not really specific. It's like you flip the sign when you're dividing or multiplying
By a negative number, yes, that turns an inequality. So it's multiply or divide.
Yeah.
Okay, then let's do this. Let's pop over to the back and let's make a challenging example. We are going to solve this logarithmic inequality. Log base 1/2 of 2x plus 5 is greater than or equal to log base 2 of x plus 3. So, before we do anything, want to decide on the domains? That way we automatically know which domain we have to be looking at, because it'll be the more restrictive one. Okay, let's go ahead and decide our domains first. We know that 2x plus 5 has to be positive, and we know x plus 3 has to be positive. Subtracting 5 and dividing by 2 gets us negative 2.5. Subtracting 3 gets us negative 3. The left domain or the right domain? Which one allows less values? This one allows less values. This is negative 2.5 and everything to the right of negative 2.5. This is everything to the right of negative 3. That means you're allowed to use negative 2.9, but you're not allowed to use negative 2.9 for this. So this is our more restrictive domain. Whatever our answer set is, has to be greater than negative 5 over 2. Okay? Awesome. Now, one of the two bases is greater than 1, but the other is not. So this one, we're going to use our rule and put a negative sign on the front. Cool so far? Okay, let me tell you what we're not going to do. We are not going to divide by negative 1, because that won't help us. If you divide by negative 1, now you have a negative in front of this logarithm, and you'll always have a negative in front of a logarithm. So you can't leave it there. What are you going to do instead? Make it a negative exponent of the argument, which looks like this. Now we have the ability to cancel our logarithms with exponential base 2 on both sides. What color do I want to use? Yeah, sure, I'll write in purple, whatever. Exponential base 2 here, exponential base 2 there, and those cancel out like that. Now I'm not going to leave this as 2x plus 1 to the negative 1. So instead, I'm going to write it as 1 over 2x plus 5. And we are ready to rock and roll. What do we do now? Multiply, because we don't want to deal with the fraction. We are going to multiply both sides by 2x plus 5. And remember, because 2x plus 5 was an argument, the assumption is 2x plus 5 is a positive number, which is why we don't have to wonder about it switching the sign over, because the assumption is already that 2x plus 5 is positive. Is everybody cool with that idea? Does that make sense? Okay. That gets me. 1 is greater than or equal to, and here you're going to have to FOIL. I'm going to say that since this is an AP classroom, you all know how to FOIL. Okay? It's going to get you to 2x squared plus 11x plus 15. Hey, look, a quadratic inequality. Yay! Subtract 1 from both sides. You got 2x squared plus 11x plus 14. And the inequality symbol points at it, so that is less than or equal to 0. Time to factor, yeah. So treat it as 2 times 14, which is 28. Which two numbers multiply to 28 that add to 11? 7 and 4, right? But remember, that was if I multiplied 2 and 14 together. So I have to now divide by that 2 to ensure that I didn't actually change the equation. This reduces. This does not. I'm not going to write it as 7x plus 2 because I'm trying to solve. There. This shows me that x would be equal to negative 7 over 2 is a critical value. And this shows me that x equals negative 2 is a critical value. And we would normally put those on our sign diagram, except the sign diagram begins at negative 5 over 2. That is a vertical asymptote. So this answer then cannot be used because that is less than negative 5 over 2. My sign diagram then actually does this. Begins at negative 5 over 2. And I've got one value at negative 2. This was a vertical asymptote. This is negative 2.5. So we're going to have to be a little bit tricky with the way that we plug something in. So let's grab negative 2.1. Is that okay? Negative 2.1 plus 3.5. Positive or negative? Positive. Negative 2.1 plus 2. Positive or negative? Negative. So I have a positive and a negative multiplying, giving me a negative result. And then be easy. Choose 0. 0 plus this is positive. 0 plus that is positive. 2 positives makes a positive. We found that our answer, because we wanted less than or equal to 0, is negative numbers are from here to here. And it's got the equal to bar, so it's inclusive on the negative 2. It's a very small answer set, but an answer set nonetheless. Adi, what's up? Shh. What? Would there be a time what?
On all of the examples, it's always been when negative 2 is less than 0.
You want to know if it ever goes to the left of some number?
Would there ever be an example where it's positive on that side and negative on the other?
You mean on the answer set?
Like the positive, negative, like what you have inside. Like
Or will it ever be
Both negative?
on the
Oh, on a sign diagram. Is that possible, you're asking? Sure it is. If the vertex of the quadratic sits on the x-axis and it points down, then it would be negative, negative. Or if the vertex of the quadratic sits on the x-axis, then it would be positive, positive. It's 100% possible. Yeah, it's because most polynomials will oscillate. But remember when we had graphs that could bounce off the x-axis? So if you bounce off the x-axis anywhere on your sign diagram, you get a sign repeated. So no, we want to just go ahead and always check just in case, okay? Okay. And just so you know, this was still done pretty easily because every example had the ability to be written in the same base on both sides. What if you couldn't? No, I don't think so. I'm just gonna let it bake your noodle because as far as I'm concerned, you guys are nerds enough to handle it.